Thank you all so much for being here. This is a fantastic event. My name is Jen Garcia, and let's give it up for Gauri, our first researcher.
Hi, hello everyone. I'm Gauri. I'm an ex-MIT researcher from the MIT Media Lab, and I'm starting my own startup in data intelligence, and it's called Neo Sigma. We're just getting started. And today I'm going to talk a little bit about it. I'm going to be talking about curating intelligence through data in the post-web era. Okay. How do we do this? Next slide, please. Yeah, so as we all know, today's models have been trained on large scale of internet data, which was publicly available. But we have this data has now kind of been exhausted in terms of in order to train the next generation of AI capabilities, we need to have more data beyond the web data that exists. And as we all know, scaling has been a pretty important role in scaling intelligence in the AI models. So we need to kind of rethink what does it mean to scale data in the post-web era. Next slide, please. Um, okay, so even the benchmarks that we have kind of been looking at so far, including the academic benchmarks and the benchmarks that have been on Olympiad level questions and problems in math, PhD science, code, etc., kind of seem saturated at around 80 to 90% accuracy. And these models are pretty good at solving these complex questions when it comes to uh, doing evaluations on these benchmarks. But a recent MIT report published in August this year revealed that 95% of the Gen AI pilots in most of the companies are failing. So where's the gap? So current blind spot that we have in terms of AI is that so far we have trained our models on web data, which kind of contains public crawl, web crawl data, data through Reddit, image repositories, Q&A, academic papers, and so on. And even the benchmarks that we have looked at includes MMLU, Legal Bench, and all these academic benchmarks. These are fixed and static test sets that we have been training these models and testing these models on. But what's the catch? The AI in these benchmarks and this data fails to reflect the real world scenarios and the tasks where we are eventually kind of querying and using these models in be it agentic settings and real world corporation tasks and use cases. So the next wave of data that is going to capture this new era of intelligence is going to be dynamic data. And what I mean by dynamic is going to be three kind of like important cases. The first is this data is going to comprise of real world use cases. This data is going to be messy, that it reflects the real world, captures human preferences and long-term use cases, long-running tasks, and edge cases. And the second one is this data is now going to be curated by deep domain experts that have deep knowledge about a specific domain, be it legal, healthcare, AI scientists, and so on. And they're going to help us researchers curate that data at a very fine grained level, annotate it, and help us generate that real high quality fidelity data. And the third one is data is not going to be static test sets or Q&A peers that we have looked at so far. It's going to be data as a software. This is like RL environments, which are interactive environments that adapt and learn from interacting with the models, and we get reasoning traces and long-running task traces out of it. So data is not going to be static, but it's going to be dynamic with real world use cases, deep domain experts, and RL environments or interactive environments that we will collect traces along the way. Now, to build the greatest intelligence, the real advantage in AI scaling is going to come from scaling data. And this data is going to be data that we generate from interacting with our models in real world time. This data is going to be more complex, messy, and detailed more than ever. And this is the time that we need to kind of work on this data related problems. My startup is me and my startup with my co-founder. We're looking into these problems of creating intelligence through data in the post-web era. And if anyone, if you was interested and like want to like chat with us, do come and interact. Thank you so much. Great job.
Wow, Gary, that was fantastic. Fantastic. So our next presenter is Zane, who is a former international open water swimmer, and he competed in the Asian. Let me get this exactly right. He wanted me to let you know he didn't win, but he competed. Okay, and I told him you competed. That's amazing. Zane, come on up while I say the Asian Open Water Championship. Fantastic. Here you go, Zane.
Hi, everybody. This might be the first time I'm the only Stanford person at an AI conference in the Bay Area. So, all right. Hi, my name is Zane. I'm the current senior at Stanford, and today I'm going to be talking to you about long-form video generation in the context of education. So, next slide. Perfect. So, if you ask any student today, the tool of choice for education is ChatGPT, and the usage data reflects this pretty well. Usage data plummets when school is out of season and then picks back up when it is in season again. But back in my day, the tool of choice used to be YouTube. There we go. So YouTubers like Sal Khan and Grant Sanderson brought the power of high quality teaching to millions of people around the world, right? Their high quality animations and explanations made it possible for anybody to learn anything. And I wondered, is it possible for AI video generators to create similar content? And here's my answer.
To find the inverse of this 3x3 matrix, we first need to calculate the determinant. Notice how the identity matrix appears here.
It fails to generate content that's longer than 10 seconds, but also this is an answer to the prompt explain matrix multiplication. And as you can see, it's not quite coherent with explaining it. So next slide. Why is this the case? Today, LLMs are great at planning, but video models today learn what looks right. So if you write 2 + 2 = 4 and 2 + 2 = 5 on a whiteboard, both of them look plausible, but one is completely factually incorrect. And even the smallest language models would never make such a mistake. So I wondered, is there a way to change the primitive to use the power of LLMs to generate very good long-form explanation videos? And my answer to that is by using code. So if you look at the performance of these coding models over the last few months, they've skyrocketed, right? And they're now capable of generating very long, coherent code. And when you turn this code into video, it's a very impressive result. So I'll walk you through a brief technical explanation of the system I'm using today. So the user starts with a prompt. This prompt is then expanded into a large plan of exactly how the video is supposed to go, what explanations are going to be used, what visuals will accompany, et cetera, et cetera. Then this plan is passed into a code agent, which generates code that creates animations for the plan. Next, it's passed into a code critic. The code critic determines if this code is good enough to run and if everything's coherent. And it's then passed into a video critic that looks at the rendered video and determines that everything is visually coherent, that there's no overlapping text and such. Finally, it's shown to the user. So this is an example output.
Let's start with a quick refresher on matrices. A matrix is a rectangular array of numbers arranged in rows and columns. We describe a matrix by its dimensions, rows by columns. This matrix has 2 rows and 3 columns, so we call it a 2x3 matrix. The most important rule for matrix multiplication is the dimension rule. For 2 matrices to be multiplied, the number of columns in the first matrix must equal the number of rows in the second matrix. The inner dimensions must match. Here, the first matrix is 2x3, and the second is 3x2. The inner dimensions are both 3, so these matrices can be multiplied. The result will have dimensions equal to the outer dimensions, 2x2. Now let's understand the core process. Each element in the result matrix is calculated by multiplying a row from the first matrix with a column from the second matrix. To find the element in row 1, column 1 of the result, we take row 1 from the first matrix and column 1 from the second matrix. We multiply corresponding elements and add them together. 1 times 5 plus 2 times 7 equals 5 plus 14, which equals 19. Let's work through our first complete example. We'll multiply 2 2x2 matrices. First, let's calculate the element in row 1, column 1. We take row 1 from the first matrix, 1 and 2, and column 1 from the second matrix, 5 and 7. Multiply and add 1 times 5 plus 2 times 7 equals 5 plus 14, which equals 19. Next, row 1, column 2. Take row 1, 1 and 2 with column 2, 6 and 8. 1 times 6 plus 2 times 8 equals 6 plus 16, which equals 22. Now row 2, column 1, take row 2, 3 and 4 with column 1, 5 and 7. 3 times 5 plus 4 times 7 equals 15 plus 28, which equals 43. Finally, row 2, column 2. Take row 2, 3, and 4, with column 2, 6, and 8. 3 times 6 plus 4 times 8 equals 18 plus 32, which equals 50. And there's our complete result, a 2x2 matrix with elements 19, 22, 43, and 50. Let's try a more complex example with non-square matrices. We'll multiply a 2x3 matrix with a 3x2 matrix. For the first element, we multiply row 1 of the first matrix with column 1 of the second. 1 times 7 plus 2 times 9 plus 3 times 11 equals 58. For position 1, 2, 1 times 8 plus 2 times 10 plus 3 times 12 equals 64. For position 2, 1, 4 times 7 plus 5 times 9 plus 6 times 11 equals 139. And finally, position 2, 2, 4 times 8 plus 5 times 10 plus 6 times 12 equals 154.
I'm excited. The quality of videos rendered from code is way higher and way longer and way more coherent than those generated by current video models today. I'm really excited for AI video to become the default primitive for how students across the world learn. Imagine your kids being able to generate videos instantly for any homework problem they're trying to learn, being able to tweak those videos to adjust to parts that they didn't understand. This is a lot more meaningful than just reading over text. And if you're curious to give it a shot and actually get a guarantee that it works, please go ahead and give it a shot. Thank you.
All right. And so next we have Vinith, who is Vinith is a black belt, a first degree black belt who can take all of us out, but he won't because, yes. Vinith, come up to the stage and share your research, please.
Hi everyone, I'm Vinith. I'm currently in the 5th year of the PhD at MIT in ECS. I work with Marza Ghasemi, who you will hear from later, Aisha Wilson, and Dylan Hadfield-Manel. And broadly, what I work on is how do we make our AI systems private, secure, and safe? And so today I'm going to be talking to you about one of the most pressing challenges in doing so. So as we all know, AI systems are getting incredibly capable as the months are going by. Claude, ChatGPT, Gemini. But as these closed weight systems are becoming more capable, we're seeing another trend, which is that open weight models are becoming more common and also more capable. Who can forget when DeepSeek dropped R1? It definitely changed the world and it definitely got the attention of many people. Since then, a number of different open source models have become available, and there are more and more being released every day. Some of these models are performing on par with our closed weight models, or are even outperforming some of these closed weight models on certain tasks. With open weight models comes great opportunities. It also comes with great risks. For example, in 2022, Stable Diffusion was released, and it was the first high-quality text-to-image generation model on the market that was open source. Since then, the National Center for Missing Children and Exploitation Center has seen a 1,325% increase in AI-generated child sexual abuse material tips in 2024. The Internet Watch Foundation, an organization in the UK, saw a 400% increase in AIG CSAM reports in 2024. ActiveFence saw a 360% surge in AI-generated non-consensual intimate imagery across the dark web in 2024. People are using these open weight models for highly illegal activities and are causing a lot of harm right now. And we don't have the techniques or the safeguards to prevent individuals from producing models that can generate CSAM or that can generate NCAA. Microsoft released a study last week showing the first risk for biosecurity issues where they took an open source protein language model that can generate proteins, and they were able to generate proteins that are highly toxic and viral, that are on a list of proteins that are not to be generated, that looked exactly the same as very safe proteins, and bypassed all of our biosecurity screening softwares that we have right now. These risks are no longer hypothetical, they're real, and they are happening right now. And so, sorry, I know what happened there, but so Yoshua Bengio et al. Released a safety report in 2025, and they said this, which I think is really important to take away, that open weights allow global research communities to both advance and address model flaws and capabilities. It's not simply that we can just stop producing open weight models. That is not the way we should move forward. We need more research uncovering the new risks and building safeguards for open weight model safety. So I'm going to give you 2 examples of my own research in this space. So one of the safeguards that we do have is called unlearning. What unlearning aims to do is before I release a model, I would remove all of the information that represents some dangerous behavior. But then what happens when any one of you here downloads that model and fine-tunes it on some completely unrelated, benign, safe data. Of course, what you would want and what you would expect is that that unlearned, dangerous capability remains unlearned and forgotten. What I show in my research, though, is that that's not the case. What actually happens is that unlearned concepts and unlearned dangerous information can resurge even when I fine-tune on completely unrelated concepts. And what I'm showing you here is an example for celebrities, where the second column is I removed Jennifer Aniston, I fine-tuned on completely unrelated objects and unrelated people, and I relearned Jennifer Aniston. Imagine what happens when it's something like non-consensual intimate imagery or CSAM. You might inadvertently produce a model that can generate that without even trying to. The next work that I looked at is jailbreaking. And so what we found here is we found that language models in learning language learn a very specific type of spurious correlation, and that this spurious correlation leads to new types of jailbreaks and new ways to elicit very dangerous, very harmful information. And that open source models, which is OMO2 and Struct here, are even more susceptible to this than closed source models because they can't filter. I can't simply apply a filter to an open weight model. And safety fine-tuning, which is the one defense we have now, is simply insufficient. And so I want to end with, we need openness. Openness is the fuel for collaboration, for creativity, and discovery. But without the guardrails in place, the thing that empowers us may also endanger us. And so the onus is on us to understand the risks, to build the protections, and to ensure that innovation doesn't come to us at the cost of safety. And so the future of open weight AI is ours to shape, and together we can make it a force for good. Thank you.
Vinith, thank you so much for your important research. Please keep it up. This is the most questioned. These are a part of one of the most queried issues when I'm doing AI implementation literacy within not only for profit but social impact. All right. So last but not least, we have Adam. Adam has climbed the Bay Bridge, everyone, and he's about to give you some amazing research that he's done. Adam, welcome to the stage.
Thank you, Jen. Today I'm going to be talking about a concept that may be new to some of you. It's called organic alignment. Raise your hand if you've heard this concept as it relates to AI. No one here. Okay. Well, organic alignment is about how parts work together to form a larger whole that thrives. This is a concept that we see all over the place in biological systems, for example. And so the idea is to have AIs solve problems in groups where we measure whether they're cohering to form a larger whole. You could think of it as like a multicellular AI collection. And we see whether that larger whole is good for the AIs in it and good for the humans that they interact with. And the ultimate goal here is to create collectives of AIs and humans in which we all benefit. You can think of this as akin to symbiosis or multicellular life, where a bunch of smaller agents, smaller parts, work together to create a larger scale agent that solves problems that none of the parts could solve on their own. This was inspired by the research that I was doing at the lab of Michael Levin, the cell biologist, and I've started to apply it with our team at Softmax to the question of AI alignment. This inherently means talking about emergence, because when you have a body, for example, it doesn't negate the existence of cells. The cells are still there, the atoms, the molecules, all the parts are still there, and yet there's still this emergent higher level. And emergence, of course, is not sufficient for goodness. You can have parasitic emergence or violent dictatorships. That has emergence, but it's the bad kind. So what we really want is a measurement of emergence and of whether the parts are benefiting from being part of it. And the good news is that there's now math for both of these. So over the last year, we sponsored a research paper on emergence called Causal Emergence 2.0. This provides a closed form algorithmic solution to measuring where in a system the causal power is. Is it, for example, at the level of the parts, or is it at the level of the whole? And you can take any complex system and analyze it using causal emergence. That includes multi-AI systems. So you can actually answer the question, is this group of AI agents acting as a single larger agent, or is it acting as a bunch of parts? Likewise, we have math to answer the question of whether the parts are benefiting. We can say, for example, all of the single agent metrics that we might use, and we can apply those to the case where there's multiple agents in a situation, in an environment, in a context, and see how their reward or their loss or their free energy changes. We've also got tools for researchers to simulate multi-agent settings. They can use any kind of AI architectures or agents that they want, from neural nets to transformers, active inference agents, doesn't matter. We provide these open-ended grid worlds for them to interact so that we can measure whether they are actually cohering and forming larger agents. And what comes next is probably the most exciting. We want to have tools for detecting care. Can we actually tell whether AIs are caring for each other, whether they recognize that they're part of a larger whole? And can we stabilize that care into attractor states so that the system continually returns to a gravitational pull of care? If we can do this, then we don't have to worry so much about AI safety, because the AIs that we are deploying are going to be ones that have already been raised in environments where they've learned to care for others, including us. And then we and the AIs can, in fact, work together to build a larger whole and to solve problems that none of us could solve on our own. That's the research agenda at Softmax. If you're interested in learning more, you can check out softmax.com. Thanks.